Here is a combined summary of the 4 pages. The paper explores the generation of arbitrary superpositions of N00N states using an asymmetric nonlinear Mach-Zehnder interferometer, ANLMZI, which is crucial for attaining Heisenberg-limited sensitivities in quantum optical interferometry. The ANLMZI's nonlinearity arises from a chi-3 self-Kerr interaction on one of the intermediary modes, allowing for tailoring superpositions of N00N states weighted by the statistics of any single-mode pure state. Inverse engineering techniques are introduced to extrapolate optimal transformations for generating N00N state superpositions, enabling the probing of means to generate states with desired quantum properties. The authors highlight the significance of N00N states in quantum metrology, where exploiting quantum characteristics like entanglement and squeezing enables highly resolved and sensitive measurements. The paper also discusses parity-based measurements, which have been shown to yield the minimum phase uncertainty, saturating the quantum Kramerau bound, for all path-symmetric input states. The ANLMZI is characterized by one intermediary mode passing through a chi-3 self-Kerr medium, aiming to generate arbitrary N00N state superpositions weighted by the statistics of any single-mode pure state. Furthermore, the authors investigate the extended Hong-O-Mandel (EHOM) effect, resulting from mixing coherent light with Fock states at a 50-50 beam splitter. This leads to a central nodal line, CNL, in the joint-photon number distribution, where correlated photon number states destructively interfere. Pseudonodal curves, PNCs, are also observed, occurring when one port of a beam splitter contains a state of definite even or odd parity. The authors then propose a scheme to generate superpositions of N00N states weighted by the coefficients of any single-mode state, using the ANLMZI and inverse engineering techniques. Starting with a general Nefodin-Fock state, they utilize the Schwinger realization of the SU Lie algebra to express two boson modes in terms of an angular momentum state. Here is the combined summary of pages 58 of the research paper. The authors derive the state coefficients gamma, n, in after a sequence of transformations, including self-Kerr interactions and linear phase shifts, which result in an antidiagonal linear Mach-Zehnder interferometer, ANLMZI. The state coefficients are shown to be gamma, n, in equals 1, square root 2a pi, 4 for n equals n, I, square root 2a pi, 4 for n equals 0, and 0 otherwise. This transformation can be applied to any superposition of Fock states, mapping the state to the axes of a two-mode distribution via an ANLMZI. The authors also consider the case where both intermediary modes pass through a cross-Kerr nonlinear medium, described by the unitary operation U, A, B, cross-Kerr, kappa, equals E caret, I kappa AB. The state prior to the second beam splitter is modified, and the phases work out differently, resulting in an independent phase shift. A general technique for numerically inverse engineering N00N state superpositions is outlined by working backwards from a beam splitter. Starting from a two-mode state, psi equals n array summation infinity n equals 0 n array summation infinity sin n equals 0 cn, and na, in B. The state interacts at a beam splitter, resulting in a final state, psi f equals u, a, b, bs, psi. For each total photon number n equals n plus n, there is an antidiagonal along the joint photon number distribution. The output state probability amplitudes are predetermined, and the system of linear equations for each value of n can be solved to express the initial state coefficients in terms of the axes probabilities, an. A method is proposed for mapping single-mode pure states into superpositions of N00N states using a non-unitary transformation matrix T, A, B. This matrix is expressed as a sum of boson mode operations, which can be realized experimentally through photon subtraction, addition, or other state reductive measurements. The transformation matrix T, A, B, is demonstrated to map a single-mode pure, thermal, state into a superposition of N00N states. The inverse engineering technique is also applied to find the transformation matrix T, A, B, that maps an initial state into a desired output state. The Schwinger representation of the SU-2 algebra is reviewed, where Hermitian operators Jx, Jy, and Jz are defined, satisfying the commutation relations of the SU-2 algebra. These operators define the Casimir invariant J², crucial in representation theory. The action of angular momentum operators on states, J, M is discussed, essential for understanding beam splitters. The beam splitter transformation is represented as a rotation in SU-2 space, a fundamental concept in quantum optics. The Wigner d-rotation matrices are introduced, describing the behavior of beam splitters. Matrix elements of an arbitrary rotation, including Euler rotation and Wigner d-rotation elements, are reviewed. The Wigner d-rotation elements are connected to beam splitter coefficients F, N, M, P, theta, used in the extended Hahn-Ohmandel effect, providing a deeper understanding of beam splitters in quantum optics. The concept of quantum-enhanced interferometry is discussed, referencing various studies on non-classical light in interferometry. The importance of entangled coherent states, which achieve the Heisenberg limit, is highlighted. The paper cites works on creating large photon number path entanglement and quantum non-demolition measurement. The Wigner-Yanez skew information is formulated mathematically, quantifying the quantum Fisher information. The authors express the Wigner-Yanez skew information in terms of hypergeometric functions and note the numerical conformation of state coefficients. The nonlinear phase shift is considered in the calculation of the Wigner-Yanez skew information, leading to cancellations of off-axis probabilities. The study on analytical formulae for numerical evaluations of Wigner rotation matrices at high spins is referenced. This section provides a comprehensive review of mathematical tools used to describe beam splitters and quantum-enhanced interferometry.